Okay, we're starting.
That's usually what I do.
That's bullshit.
I spent $50 in What? 600.
We're moving on to 2.3, which I'll kind of do at the same time as 2.4. This type is called derivatives.
Is it 1 over negative 16?
Yeah.
And their applications. So now we're going to talk about one of the main guys in calculus, the derivative. It's a very important kind of operation. And I can't wait till I get over this thing. Oh, by the way, we don't have class on Tuesday. Right? So on Monday it's President's Day and the college is closed. And on Tuesday they made that a Monday schedule to make up for that Monday. And so we won't have class. So the next time I'll see you guys is Wednesday. And I'll have your tests back by then. I just wanted to announce that before I forget. Okay, now back to the, yeah.
So will the quiz be on Wednesday? Will we have a quiz or?
Yeah, we'll just move the quiz to Wednesday instead. Okay, so now back to this idea. So we spoke a little bit about well, I kind of mentioned it, kind of what calculus was about and what it's the study of, and I told you that it was the study of really limits if you were forced to use one word, but if you could expand on that, you would say it's the study of derivatives and integrals and their applications, and we're going to look at one of these guys. So I sort of want to tell you what the goal of developing a guy like this was in the first place. See, mankind had many more problems, but there were two problems in particular that mankind needed to know how to solve pretty early on. And one of these problems was the so-called the rate problem, right? So if you look around in life, you'll notice that things change. Things break down over time. Populations grow, radioactive elements decay. Over time, things change, and sometimes how fast things change is going to be important to you because you're going to want to be able to make predictions and plan for the future. And if you see changes that are happening now, you'd want to be able to say, okay, what is that going to mean 5 years down the road, 10 years down the road? And how are things changing and how fast they're changing, and what would this mean for my business or for my house or for this population or for this country or for whatever, right? So there was this idea of needing to be able to measure rates of change. Right, because in life everything is changeable. You needed to know how fast something changed in order to make predictions about it. So that was the so-called rate problem. Really having a one-size-fits-all, a very sophisticated tool or machinery that you can slap on top of something you're measuring, and it will tell you this is how fast it's moving. Okay, so that was the answer to that was the derivative. The derivative was that tool. There was another kind of problem that was very important to solve, and that was the so-called area problem. And that's basically figuring out how much space something takes up. So finding the area of a rectangle, for example, is pretty easy. But let's say you were some sort of farmer, you owned a plot of land. It's not exactly a rectangle. It's this weird shape. But you still would want to know how much land you own, right, for various reasons. Whether you want to plan on how you want to use that land, or you want to make sure that the government is not overcharging you on taxes, saying that you own more land than you actually do, things like that sort. So knowing how much space something takes up was very important. And to actually answer that question, the mathematician's answer was called the integral, which is something that we'll look at towards the end of this lesson. But the derivative is the answer to the first kind of problem, the rate problem. Figuring out how fast is something changing, measuring rates of change, and then figuring out what this means, and making predictions based on your ability to do that. So that's kind of what half of calculus is about, so-called differential calculus, the parts that deals with derivatives. It's really talking about rates, measuring how fast something's moving. It's kind of knows that. And that leads us to derivative. And so now we want to think, how would you go about measuring how fast something changes? Well, we've actually discussed a lot of ideas so far that might help us towards this. For one, let's start with what we know. So the goal, let me just put that out there, that our goal is to be able to measure a rate of change. And, by the way, to do so instantaneously is the phrase that you might use here. Because it turns out that we do know how to measure one kind of rate of change. That was the average rate of change, right? How something happens over time. But usually for that to happen, the time had to already have passed for you to be able to know what the first point is and know what the last point is and then measure the change. And so sometimes you want to know about in the moment how fast something is changing. That's called instantaneous rate of change. Okay? So that's kind of the goal that we want. And so now we can talk about some things that we already know. Right? One, we know about the average rate of change. But for us, it's not good enough, basically. It's not good enough for our purposes. If I want to look at something now and figure out how much is it changing right now, I don't want to have to measure now and then come back 2 days from now and measure it again and find out how did it change over 2 days and kind of work. I want to know how fast is it moving right now, right? But we do know how to measure it over a period of time, and we might be able to use that to our advantage. So that's one thing we know. We also know about the idea that I introduced when we're going over equations of lines. We know that slope can be used to measure rates. Right? So there was a time when I told you about the equation of a line. I gave you an interpretation on the y-axis and on the x-axis, and we figured out that when we measured the slope, it actually gave us the speed or the velocity at which we were moving. And so there's this idea that if you're measuring the slope of a straight line, it can tell you how fast one variable, the guy that's on the vertical axis, is moving with respect to the guy that's on the horizontal axis. So we know about measuring changes over a vast period of time, and we also know about the power of a slope to measure rates. And so we kind of want to put these two ideas together and come up with something a little bit more sophisticated that can allow us to measure a rate of change instantaneously. So here's the idea. So this leads to the need for a so-called tangent line. Right? So let's actually look at some examples here. So here was a picture when we had some function that was doing whatever between A and B. And we could actually make a line going through those 2 points, and we realized here that the slope of this line, that was equal to the average rate of change. Such a line, by the way, has a certain name. It's actually called a secant line. So if you ever see that mentioned in your textbook or somewhere else, that's what that line is called. It's called a secant line. What we're after is something like this. So we have that function doing its thing, and there's a point here, which is at point A, for example. But I want to somehow be able to draw a line just at that point, not really connecting to some other point. I want to know what is the function doing right here. Right? So we want to go from a situation where we need 2 points that are at various times to be able to do that idea with 1 point. Right? So what we're after here is called a tangent line. Right? And the slope here would give us the instantaneous rate of change. And why does this matter? Here's the idea. tangent line should be drawn in such a way that it approximates the function. Locally. So in this situation where we have our thing doing its thing, and there's a line here, the idea is, if we were to zoom in there, what we want is, for when the function is doing something, the tangent line is doing very nearly the same thing, right? And the more you zoom in, the closer together these lines become. And what that gives us is somehow we can actually use what we know about the line to talk about the function. It now becomes an approximation for the function. The difference between what the line is doing and what the function is doing isn't that different. And the more you zoom in, the more true this would become. You want to be able to draw a line going through one point in such a way that this idea happens. And so why would that matter? Well, I don't know how fast this random thing is moving, but I do know how fast that straight line is moving. I know how fast it's moving by just measuring its slope, just using y2 minus y1 over x2 minus x1. So by knowing how fast this line is moving, it will be the same as knowing how fast this function is moving when I'm in that little region, right? The more I zoom in, the better fit the line is to the curve. So the idea is by knowing about the rate of change of the tangent line, we will know about the rate of change of the function in question. So this was the idea. This is how we decided to tackle the problem. So there was one situation where we could find the average rate of change. That wasn't good enough. We wanted to know what the curve was doing in an instant. So we wanted to get to a situation where we can actually draw a line that's moving through a single point in such a way that if I keep zooming in, the equation of the line and the equation of that function are pretty much the same thing. And in that way, I can use what the line is doing as an approximation for what the function is doing. And in particular, I can figure out that the slope of the line and the speed of the function at that point would be the same. And so then I could say how fast it's moving at a certain instant. So let's actually figure this out. So here's how we're going to do this. So here's my function, it's doing whatever. This is f of x. Here's the point that I care about. That is x. My y-axis, this is my x-axis. The idea being now, we're going to use something that we know a lot about to figure out something that we don't know a lot about, which is a very common thing for math. You use your solution to a very simple problem and you kind of modify it to be able to solve more complicated problems. So the idea is we do know how to actually draw a line through 2 points, right? So I can actually get that. So let me say I pick another point. Let's say it's h, a distance of h away. Right? And so I know that line. So this guy here is a secant line. And so here's how I'm going to get to the situation where I'm only drawing it through the straight line through 1 point. What I'm going to do is the following. I'm going to start to shrink the distance between these 2 points. My goal is so that I can move this point closer and closer to this point, so that when I'm drawing the line through 2 points, it's kind of like drawing the line through 1 point, right? And you can notice that if I start inching this point closer, I keep getting another straight line, and then I inch it closer. I get another straight line, and then I inch it closer, to the point where I get so close that now drawing that line is going to look kind of like the curve when I zoom in. Right? See, that's the idea. I'm going to start pushing this point close to that one. I'm going to let this point approach that one, and I'm actually going to think of this distance h as approaching 0. So now the question is, do we actually have a mechanism to actually do this, to let something approach a certain value? Yeah? Limits. Now limits come into play. The idea that I want to take something and I want to inch it closer and closer towards something else, that is something I can do with a limit. So here's what we want to do. So we start with the slope of the secant line. Which in this case, we actually did this before. This is f of x, where that is x. If this is x plus h, that would be f of x plus h. So the slope of the secant line is going to be f of x plus h minus f of x over h. That's y2 minus y1 over x2 minus x1. That's the expression I would get. And now, let h approach 0. So the 2 points essentially become 1. So this ends up being what we call a tangent line because it only goes through a single point. And so we end up with this, the fact that the slope of the tangent line would simply be the limit as h approaches 0 of f of x plus h minus f of x all over h. This is a very important limit. This is a very important limit. And we give it a name. So that leads us to the definition where I'm going to tell you the name. It's called the derivative. So the name here is called the derivative. So that's what the derivative is. It's a limit. It's the limit of the difference quotient as the denominator goes to 0. And so now you can see, for example, why there were situations where I was asking you to simplify a difference quotient, and I told you it was very important that you were able to cancel that h in the denominator. It is because at some point in the future, we're going to want to be able to plug in h equals 0. And why this expression is important is because now you can see it's really measuring the slope of a line, and the slope of a line is attached to how fast something is changing. And so we can use the slope of a line to figure out the speed at which something is changing. And so the expression for a slope ends up being a very important expression in calculus. And it's called the derivative. So this limit is called the derivative of the function f. So let's actually write that down. So let f of x be a function derivative of f of x at x is given by the limit provided it exists. Because it's a limit, it's possible for it not to exist. So this is, we're defining the derivative of a function at a certain point, at x. It's given by this guy. And that's the notation. This notation here, this is kind of like an apostrophe. So it's a little notch. It's called a prime, so this you'd read this as f prime of x. And it basically means you're taking the derivative of the function f with respect to x. So let me actually write about some notations here. So this is right f prime of x. Since the apostrophe is since the name for this is a prime. Right? This is Newton's prime notation. So back when Isaac Newton was developing calculus one summer when he was trying to win a bet, this is the notation he used to describe the derivative. And so this notation is attributed to Newton. And so once you see a little notch on a function like that, it means you're taking a prime of the function, which means you're looking at the derivative of the function. There was another mathematician who history credits being able to develop calculus. He developed calculus independent of Newton, and he actually used different notation. So there's his notation here. It's called df dx, or dy dx. df dx d. That's how it's read. And it also means this means the derivative of y with respect to x. If you want to write it out, that's how you say it. So it's the derivative of y with respect to x. Call it dy dx. And it also means a derivative. So this is called the Leibniz notation. For the derivative. So you can have the Newton's prime notation and the Leibniz notation. We can use these interchangeably. They will be used interchangeably. Probably for me, I write the prime notation a lot of time because it's just easier to write. It's easier to just write a notch on something as opposed to writing blah, blah, blah. But this notation is actually very useful because there are many contexts in which you can literally treat it like a fraction and you can multiply by a dx and move stuff. It's a very useful notation. You can actually figure out a lot of things by just breaking up the notation into fractions into convenient ways. Okay. So there are two main notations that we will use. So I can use simply as say dy dx or df dx or f prime of x. These both refer to this limit called the derivative. So, and this is of course important, so this is something that you need to memorize. I think I asked this on a bonus, a part of the bonus on the test, where you actually describe what the derivative of a function is as a limit. This would have been the answer. So let me leave that up for a little bit more. That's a very important thing. So we'll try to get through a couple of examples, maybe one, and then we'll do a bit more when we get back. But for now, there's a certain way I want you to think about derivatives. From now, moving on to the future. So when you see something like f prime of x, right? So I do want you to think of, oh, that just means a derivative. But that word might not mean much to you. Okay, it's a derivative, so it's that random limit. But there are ways that we can interpret this thing. So one way is to think of it as what it is by definition. It is actually the slope of the tangent line. To f at x. That's one way you can think of a derivative. So when you're thinking of a derivative, it's one way to get to the slope of a tangent line. So there are some times when a problem might ask you specifically, find the slope of a tangent line, you should know that you should be using a derivative. So that's one way you want to interpret a derivative. It's something that gives you the slope of a tangent line. And in fact, you can think of this as the slope of the function itself, the slope of f of x at x. Right? And it gives you, basically it's going to give you a formula for this. Right, so your f prime is going to be some other function of x, and it's just going to be a function that, if I plug in the x value, what it does is it gives me the slope of the function at that value. You can also think of it as the rate of change. Instantaneous rate of change. Let me do that for emphasis. It's the instantaneous rate of change. Of f at x. So if I want to know how fast this function is moving at that particular point, this is the function that's going to tell me that information. You can also think of it as something like how fast y equals f of x is changing in relation to x. So there are times where you can think of it as something like a speed or velocity, etc. Right, these are all interpretations that we can put on this function. Any questions so far? So I'm just talking at you. That's the important thing. This is what we need to memorize. It is called the derivative. That's called a prime. This is called f prime of x. It's equal to this limit. And provided it exists, it gives you the derivative of the function, which we can interpret in several ways. Important ways you want to interpret it is in terms of the slope of the tangent line at a point, and the fact that it will give you the instantaneous rate of change, or how fast the function is changing with relation to the independent variable. Let's actually do an example. We're going to find the slope of this function at the point where x equals 2. We're going to interpret the answer that way. Let's actually do this example. So we know the slope equals the derivative. So this would mean what I'm after is going to be y prime. Okay, so I'm calling my function y, so I'm going after y prime. So what y prime is, this is the limit as h approaches 0. Your f of x plus h minus f of x over h. This is the limit as h approaches 0. So what is f of x plus h here? X plus h all squared minus x squared all over h. Now this is a kind of calculation that we've done many times before at this point. X squared plus 2xh plus h squared minus x squared. These guys would die. You want to cancel that h because you want to take the limit. And so here there's a common h that I can factor out. That's 2x plus h over h. H is cancelled. So this would give me the limit as h approaches 0 of 2x plus h. And so that is 2x. That is, f prime of x here is 2x. So if I have the function y equals x squared, it turns out 2x is going to give me a formula for the slope. We've gotten that function 2x. So now, it asks me at x equals 2, so let's actually do that. At x equals 2, we would get that f prime of 2 is just going to be 2 times 2, which is going to be 4. And so here are some interpretations that we can put on this. Right, it says interpret your answer. One is that you can think of 4 is the slope of the tangent line. At x equals 2. It's also how fast the function x squared is changing at that point. Right? Meaning if I actually put units on this, like miles per hour, right? How fast it would be moving is at a speed of 4 at the point when we're passing through x equals 2. And we can actually draw that. So it's like here, got my y equals x squared. So I pick the point here where x equals 2. It's that point. It's saying that if I want to draw a tangent line to this function, passing through that point, the slope of that line would be equal to 4. Can I erase this? You guys help with this?
Yeah.
Sometimes you want to find the equation of the tangent line. How would I actually go about doing that? Let's say, so I have this line, and I know the slope is 4. How do I find the equation of that line? I know the slope, so what else do I need? Yep.
The coordinate?
Like a coordinate, like a point. How can I find the point?
Well, you already did the x.
Right, well I know it passes through x equals 2, so I just have to find the corresponding y coordinate. And I know that this line actually touches the curve x squared at that point. So the y value for x squared is actually going to be the y value for the line at that point. So here, you can find a point. So when x equals 2, we know that our y is equal to 2 squared, which is 4, because I plug it into the function x squared. So this means 2 comma 4 is on the line. This means our tangent line will be, we're going to use y minus y1 equals mx minus x1. Y minus 4 equals to m, which is also 4, x minus 2. And that's actually the equation of my tangent. Now I could also solve for that by solving for y. But if you're asked for the equation of a line and I don't specify what form, it's okay to leave it in that form. But you could say also this is y is equal to 4x. This would be minus 8 plus 4. This is minus 4. And that would be the equation of my tangent. Let's actually find some more functions here. Y equals x, y equals c, where c is a constant. Y equals the square root of x. Find the slope of that function. Y equals 1 over x. We're not going to do these now because we're pretty much out of time, but try them on Tuesday when we're supposed to be having class. But you're fine. And we'll go over these on Wednesday and also talk a bit more about derivatives. The equation of the tangent line. Y equals 3 minus 1 over x at the point where x equals 1. And we'll stop there for now. So today we defined derivative, which can tell us about the instantaneous rate of change, and the slope of the tangent line, which hence we can find the equation of the tangent line. And we're actually going to use this in a lot of neat ways to answer all sorts of questions. And we'll stop there. We'll see you guys on Wednesday.